Section 5.2 is going to discuss spherical coordinates, and if you recall from the last section, we talked about how we can convert back and forth between our common rectangular coordinates and then this rotational polar coordinates that we introduced. Spherical coordinates are just going to move that to the third dimension. So spherical coordinates, if you want to have a definition for them, we use the Greek letters rho, theta, and phi to define this. So again, Greek letter rho, Greek letter theta, and Greek letter phi. So these coordinates of a point P in the three-dimensional space are given such that rho, like I said, this is the Greek letter R, is the radius, which would be the distance from 0 to P, and it's written this way kind of as the absolute value because absolute value tells you your distance from the origin to a point. So is the distance from the origin to the point P. Theta is the angle of rotation on the XY plane. And phi is the angle of rotation between the positive z-axis and the line from O to P. So let's take a look at exactly what that means. If we were to draw that out in three-dimensional space, if we have our z-axis going from up to down, and then our xy plane is kind of coming out of the page, if you will. So here's our x, here's our z, here's our y. Again, these are all supposed to be perpendicular to each other. Now, if we have some point P, we'll locate it here, and we draw our line from the origin to that point. So this is our radius rho. If we drop a perpendicular in the xy plane, so this here is supposed to be a right angle, then your angle here from x to y is theta, and then your angle up here from the positive z-axis down to the point is phi. So we're coming across and then we're coming down. If you were trying to convert these to coordinates, you could draw this one back to your x value, you could draw this back over to your y value, and you could draw this to your z value. So let's talk about how we would do those conversions in the formulas. Like I said, we've got triangles here, so that's all we have to really do. If you want to go from Cartesian to spherical coordinates, it's actually pretty straightforward as far as finding the radius. It's still going to be the Pythagorean theorem, just kind of a step up. So from Cartesian or rectangular to spherical, like I said, rho squared is just going to be x squared plus y squared plus z squared. And again, you could solve that if you wanted to for rho and just say that rho is equal to the square root of x squared plus y squared plus z squared. The other pieces aren't too bad. Again, we've got theta and phi here. If you, again, have your x, your y, and your z coordinates here, you can find theta. You can see here that theta is related to x and y, but before you do that, you actually have to find what phi is. So again, if you look at the triangle here, if you kind of move this out, if you're just looking at your z coordinates, phi is here, rho is here, this is your z coordinate. So you have your radius, you have your distance here, z, and you have your angle. So you notice here that, again, if this is a right triangle, you've got your adjacent piece and your radius, so that would be cosine. So cosine of phi is equal to z over rho, or if you want to solve for phi, it's just going to be cosine inverse of z over rho. So these are really important that you have to do them in order because you need rho in order to find phi. And that's going to also happen as far as the theta is concerned. Since we have x and y, one way to look at this is to take our tangent of y over x. Just keep in mind, though, that it is possible that x is 0, depending on where you are here. And if x is 0, then you're going to have to pay a little bit more attention as far as things being undefined. So we'll give an alternative formula that you can use for that. Essentially what you do is you drop this line here, you use rho and z and get this line right here and use it as the radius. So two ways to find theta. One way is to say that tangent of theta is equal to y over x, or that theta is equal to tan inverse of y over x. The other way, again, like I said, if you wanted to, is to think of this as cosine of theta is equal to x over our rho sine of phi. So if you solve it that way, theta could also be thought of as cosine inverse of x over rho sine phi. So that's how we convert from Cartesian to spherical. Going the other way, again, we just kind of reverse some of these equations in a way. If we again look at the triangles, if we've got all of these angles here, we want to find x, y, and z. It's easier if we start with z here because we have that phi. Again, z is going to be our adjacent part here, so z is essentially just rho times cosine of phi. So rearranging this formula here, we get that z is equal to rho times the cosine of phi. So that gives you this distance here. If you want to get this red distance here, then that's just sine of phi times rho. So again, now we've got our hypotenuse here, so we could get x and y. And that base of that triangle we'll call D is going to be rho times the sine of phi. So using that piece, again, this is our D here, that diagonal, if you will, out there. So again, if you look at these opposite and adjacent, if we're looking at theta here, if we kind of drop the triangle this way, x is your adjacent and y is your opposite. So cosine of theta is x over, again, D, so x over rho times the sine of phi. And if you rearrange that, you get that x is equal to, just multiply that up to the other side, sine of rho times the sine of phi times the cosine of theta. And similarly, sine of theta is equal to y over D, which is y over rho times the sine of phi. So y is equal to rho times the sine of phi times the sine of theta. So let's try these out here. We're going to do some examples. This first one, we're given stuff in spherical coordinates. We want to convert it to rectangular coordinates. So we're going to be using these formulas here. We'll just start with x. X, again, we've got rho, theta, and phi. Make sure we have them in the right order. So x is going to be rho, which was 2, times the sine of phi, which is our pi over 3, times the cosine of theta, which is our pi over 4. And if you want to, you can write these in order: rho, cosine, theta, sine, phi, if it helps you to remember to keep things in order a little bit better. So if you do that, you come out with approximately 1.225. Y, again, 2 times the sine. Y is a little bit easier because they're both sine. Pi over 3 times the sine of pi over 4. And this is also going to come out to 1.225. And then finally, z is equal to 2 times the cosine of pi over 3. Cosine of pi over 3 is 1/2, so we just get 1. So we always want to make sure we write our coordinates, again, x in the ordered triplet form. So we've got 1.225 for x, 1.225 for y, and then 1 for z. So if we wanted to plot this, because it asks for that as well, we'll draw our axes in here. And again, x, y, and z. 2 is usually kind of the last thing we're going to do. Our theta, again, along here, we've got a 45-degree angle between x and y. We've got about a 60-degree angle. And so if you kind of drop your perpendicular there, you can see that. And again, if we go out 2 units, we'll just call this 2 units. So this is about where we are. So if we wanted to make sure we were on the right track here with our 1.225 and 1.225, since we have that 45-degree angle, that makes sense. Those are both equivalent. And then z is 1. So if we were to kind of draw this over here, we would have it about 1. And again, it's not the best drawing here, but you can see that these distances are a little bit further than that one there. So at this point, I want you to look at example 14, go through, pause the video, try that example, and then enter your answer in the online system. And then resume the video. We're going to look at example 15, and that's working from Cartesian back to spherical. And we have to be a little bit more careful with this because we're using those inverse functions, and those get a little tricky when it is in the calculator. So we want to make sure we check our coordinates when we're done. So in this case, again, with our formulas, rho was equal to the square root of 0 squared plus 2 square root of 3, that whole thing squared, plus -2 squared. And if you put all of that together, you get the square root of 16, which is just 4. Then we've got phi is cosine inverse of -2 over our rho that we just found, which was 4. So cosine inverse of -1/2. And we end up with 120 degrees, or 2 pi over 3 if you want to put it in radians. And finally, theta, if we do tan inverse of y over x, you can see how we have that 0 there. So we can either try to figure out if it's at 90 degrees or 270 degrees, or we can use the other formula, which was cosine inverse of 0 over 4 times the sine of 120 degrees. And cosine inverse of 0 is just 90 degrees or pi over 2, depending on which you prefer. So let's first look and see if this works as far as plotting, make sure everything's in the right spot. So we'll draw our coordinates again, and in this case we've got 0, so we're not moving on the x-axis. Y is 2 radical 3, which is about 3.46. So 1, 2, 3, so 3.46, somewhere about there. And z is -2, so 1, 2. So this is dropping down 2 units. So this is our point here. And let's see if that makes sense with what we have. We have 4 units away, and that's reasonable based on where that looks like. We've got a phi, an angle of 2 pi over 3 or 120 degrees. That makes sense here. And then we have that pi over 2. Again, this is supposed to be directly below the y-axis, so that makes sense that our angle here was 90 degrees. We got all the way over to the y-axis and then drop down. So that makes sense there. Again, we always want to write our answer in triplet form, so 4, and then make sure you're careful here, theta comes next, so 90 degrees, and then phi, so 120 degrees. Or if you want to use the radians, 4 pi over 2 and 2 pi over 3. So again, I want you to complete example 16, enter your answer in the online system. And then the last thing we're going to talk about for this section is how we can graph a few things. We're not going to get too carried away with graphing, but it is good to kind of talk about just some of the general or the basic shapes. If, for instance, we have rho was equal to some constant, we would end up with a sphere. And I'll try to kind of draw it on here, but I will admit that I am not the best artist. So you guys can kind of go with me there on that one. Again, so a constant radius is going to give us a sphere. That makes sense because that means any point out here is falling on that sphere, just like a circle is a constant radius and two-dimensional. If theta is equal to a constant, then we end up with a plane, and that plane in this case is just going to be going through the z-axis. And again, it's using that theta there. So wherever theta is, any line there, again, coming out of the z-axis is going to have that rotation. And so we can just say that every line there is going to just kind of stack up there, and you're going to get this plane. And then finally, if phi is constant, and this one's the one that's a little bit maybe trickier to see, phi is that angle out from z. So if we draw that constant out from z, then we actually end up with a cone. And the top cone, so again, this would be our phi here, or here. Top cone, if you have one up top, then you know that your angle was between 0 and pi over 2. And if you're down here in this lower part, then it is you're between pi over 2 and pi. So again, if you think about rotation, you get from 0 to 2 pi would get you to the y-axis, and then pi over 2 to pi would get you back down to that other axis. And it doesn't make as much sense to kind of go back around because you've already created those with the ones that we started with. So that's going to conclude our video on section 5.2.